All right, second lesson of the transformations unit. This one's about translations. If you didn't notice, unit 1 was all about reflections. Unit 2 is all about, or sorry, day 2 is all about translations. All right, so we need to tell you what a translation is. We'll do that by telling you what a vector is and define translations in terms of their pre-images and images, with and without coordinates. All right, a transformation, I don't really like the word glide here. A transformation that, can I change that to slide? Would it bother anybody if we just went ahead and called this slides? We use the word glide for something else. All the points in the plane, the same distance in the same direction is called a translation. And really, the nickname for translation has always been slide. Sometimes they're called slide transformations. If a reflection is called a flip, a translation should be called a slide. If a translation maps A to A prime, B to B prime, and C to C prime, points A, B, and C slide. Glide isn't really wrong. It's just I like using glide for something else we're going to do this unit, so I'm going to say slide. Along parallel or collinear segments. And all those would be the same distance. So what's going to happen here? Slide's a good name for it. Point A is going to slide over somewhere to point A prime. That could look like a translation. Well, from just one point, you can't really tell what a translation means. Let me do another point. All right, so point B over here is going to go, in my estimation, if it was going to do the same translation, B prime would end up kind of over here, and point C, if it started there, would kind of go around here. What this is saying is if all of these are under the same translation, and I tried to do it so it looked like that, the trip that A took to go to A prime, like by the trip I mean the slide, the direction and the distance, it went kind of down in this direction, kind of downwards and to the right. C did the same trip, B did the same trip. So really, slide is the name of the game here. And if I connected all those points, A to A prime, B to B prime, C to C prime, all those segments, that was a really bad connection, those would all be congruent and parallel. And that's kind of what's going on here in a translation. They all go the same distance and direction, so they'll all be parallel and congruent if you looked at the before and after. In Sketchpad, of course, yes, Sketchpad has a cool version of that. Let me lock my door because that was annoying. All right, this is set up in Sketchpad. We have the same kind of Phineas looking picture. If I hit the translate button, notice what it does. It slides over, and it slides over by what was defined by this little segment right here. I can move this out of the way. It wouldn't change much. And what's cool about Sketchpad, of course, is it's dynamic. I can move these things. So this figure over here on the right here is a translation of the figure on the left. If you change the definition of that translation, like all of a sudden now I want it to be this translation, it's going to do that. So all of the points, so this little point right here, when it did the translation, it ended up over here. It's like the dance. When it did the translation, do the translation, everybody do the translation. It's doing this trip right here. It's going from this point here to this point at the end. All those points that in fact, I could pick this up and I could move this and I can show you. That point did the translation and it went right there. This point up here did the translation, ended up right there in that little corner. This point did the same thing and this point did the same thing. So it's really a lot like copy paste. And where you do the pasting, like or where you've lifted up your copy and then drug it over and decided to where to do your paste, that's the motion sort of this translation. Okay. That was the fancy GSP demo. Oh, the page is translated. Okay. Any of the vectors A to A prime, B to B prime, C to C prime, we call those vectors. It's really just like a segment with an arrow at one end. It's a distance, so it's a segment sort of, but it's what's new about vector. The difference between a vector and a segment is the vector has a direction on it. So any of these vectors that take A to A prime, B to B prime, or C to C prime could be what we would call the definition of the translation. It could be the thing that gives you enough instructions to translate any point you wanted. Just kind of like back in here, this thing that didn't have an arrow on it. But if I call this the pre-image and this the image, the location of these 2 points and kind of the location of this segment right here tells us everything we need to know about what to do to this figure to get it to show up over there. We take all these points and we go, we do that with them, which is what this is about, which is what all these little things are for. And so that's enough information. A vector has magnitude and direction. So all these little red segments, first of all, they're all equivalent because they all go the same direction. They're all parallel to each other, and they're all the same distance. Their distance is called their magnitude. Their direction, of course, is, well, their direction. It represents a displacement in the plane. It's like taking a little vacation and going from this point up to this point. So if you haven't figured that out yet, rewind and watch me do that 20 more times because I feel like I'm saying the same thing. It's denoted this, and if you can't read that very well because it's kind of stuck up against other stuff, it's the vector that's going from A to A prime, and it's this notation with a little half arrow kind of thing right there. It looks kind of like a ray notation, but it's this little like barbed fishhook kind of thing up here. That's a vector. There's other books that have other notations, but I don't think they talk about them here, so I'm not going to mention it. Okay, where A is the initial point and A prime is the final point. The magnitude is denoted by this absolute value of that, because that would be the length. And you could find this length by doing Pythagorean theorem if you're in coordinates, or if you just had like this on a number line, or if you had a ruler, you could figure out the magnitude. So magnitude is really just distance, which you could do with coordinates, or you could do it by measuring, depending on what kind of universe you're in. For that problem, a vector in a coordinate plane can be written in component form, and these are actually, yeah, they're pointy brackets, A, comma, B. So it's kind of like coordinates. And A, like the x coordinate and the y coordinate, represent how far we're going along the x coordinates and along the y coordinates to get to the ends of our vector. So it's like building that Pythagorean triangle we always built when we were doing distance. But this kind of breaks down this motion into, you know, this crazy like weird northeast motion into an east motion combined with a north motion. And by knowing this, you would know the same amount of information. Yeah. A is the horizontal change and B is the vertical change. So it's almost like recentering this vector at 0, 0. If I started the vector at 0, 0, and I performed this translation on the point 0, 0, it would end up over here at the point AB. This would be point AB after the translation of vector bracket, you know, cornery bracket A comma B from 0, 0. It's another way to think about the definition of that. A translation or slide, gosh, I'm going to argue that until I don't see that anymore. Okay, in a plane is a transformation T along brackety vector A comma B, which maps any point xy to the point x plus A, y plus B, where A and B are constants. So whatever the coordinates were of this, I did this 0, 0 stuff already. So I knew the coordinates of this point. We're going to do this in the problems in a second. So we'll see this again. Whatever this point is, this point, to get from here to here, like look at the actual example, what we're looking at here. This went 3 to the right and 1 up. Whatever these coordinates are, I would add 3 to the x coordinate and add 1 to the y coordinate to figure out whatever this is. And if I did that sort of plus 3 to whatever the x was, and I did the plus 1 to whatever the y was, if I did that to a bunch of points, they would all take the same trip. They would all take the trip that's written by this red arrow here. They all take the plus 3 plus 1 trip. I could write that as 3, 1 if I was going to write that in the pointy vector notation. I could write it this way if I was going to write it as a generic kind of transformation like we were doing in the last class. Anyway, so these are all different ways we can represent isometries. Translations. A translation is an isometry, just like reflections were, meaning that when you have a figure, the one I drew on the last page is pretty good. If you had a figure like I had this triangle A, B, C, bad picture. I'm going to look back at Sketchpad. I am going to step away from the marker. Okay, in Sketchpad, if I take this figure before and after the translation, guess what? They are congruent. If I shrink this translation down to 0, you'll see that, yeah, they line up right on top of each other. So any distance before the translation is congruent after the translation. This figure, all these angles, they're all congruent in pre-image compared to image. Okay, where are we at now? On the next page. All right, now let's do some problems. Sketch P prime, Q prime, R prime under the translation described by this. So all the x coordinates are going to get 6 added to them, and all the y coordinates are going to get added like a -2 to them. This could also be written this way. This would mean exactly the same thing, in case you like that better. It means take all these points, go over 6, and down 2. So Q prime's going to be right there. I'm really not even thinking about numbers. I'm just going to take this trip. R goes 6 over this way and 2 down. And that's R prime. And P goes 6 over this way and 2 down. And so there's P prime. And to make the triangle, what I should really do is connect the dots. And I can do that now because I've done all the corners of a triangle. And hopefully you learned that in the last lesson. But that's enough to do that. Okay. Show that the distance from P to Q is exactly the same as the distance from P prime to Q prime. Well, really the best way to do that is to find what the distance is. it's kind of hard to make this argument that, oh yeah, P is 1 over and 6 up, and then you get to Q, and it's the same over here. It's easier just to find the dang distance. All right, so we'll call this X for the distance on PQ. This coordinate is, oh man, -3, -6, -7, -2, and this is -6, +4. This is 0, 2, and this is -1, -4. All right, are these distances all the same? Well, the distance from P to Q, if I did my Pythagorean theorem stuff on this, this is 1, this is 6, so we got 1 squared plus 6 squared equals PQ squared, so PQ is the square root of 37 in my head. And from P prime to Q prime, well, from P prime to Q, -1 to 1, okay, that's 1, and -4 to that's 6. Oh, guess what? It's another 1 by 6 triangle. So if I do that, Pythagorean theorem, that gives me P prime Q prime squared. And so the distance from P prime to Q prime is, believe it or not, exactly the same. Okay. Check me in the calculations if you wish. I do make mistakes on these things from time to time. Okay, could the transformation, and I think I copied another grid here because I didn't want to mess you up by looking at that 2 pictures on one graph. If you reflected PQR over the y-axis and called it P prime, Q prime, R prime, could you get there by a translation? All right, well, let's do the reflection first, and then let's see if there's any kind of translation that would take this triangle here. Reflect this over the y-axis. All right, so R is here. I'm going to travel towards there, perpendicular, keep going just as far on the other side. Okay, great. There's R prime. That was the easy one. Q prime, I'm going to travel towards the axis perpendicularly. Okay, that was 6. I'm going to keep going 6 more. That's right there. There's Q prime. P prime's down here. It's 7. It's about there. I'm going to draw nice straight lines with my cheater tool. It's almost like having a ruler. Okay, so there's the P prime, Q prime, R prime. This was the one that was formed by doing the reflection over the y-axis. Is there any translation that'll take this here? Well, okay, if there's supposed to be a vector that takes R to R prime and the same vector takes Q to Q prime and takes P, no, there's no way. There's no one vector to rule them all, you know, that has a given distance and a given direction. Well, I guess the direction they all go kind of straight to the right. But they're all different distances, like the distance from R to R prime and Q to Q prime. Like there's no one magnitude vector that's gonna work on this. So the problem is magnitude is not constant. The problem is with magnitude. Okay, well, I could do one more example. Oh, I'm almost gonna make this in 15 minutes. All right, find the translation vector for T that takes PQR, which is this one, to P prime, Q prime, R prime. All right, P to P prime, or R to R prime, or Q to Q prime. They're telling us it's all the same vector. It's a vector that looks like this. It's that direction and it's that distance. Well, it went over to the right by 8 units and up by 2. I'm going to write that this way. 8, 2. You could try that with Q. You could try that with R. They should all do the same thing. That's a 8, 2, by the way. From P prime, Q prime, R prime. Maybe I can finish this in the right amount of time. To, let's change color. From the single primes to the double primes, those all went from like here. Make sure you connect the right dots. So from Q prime to Q double prime, that's up here. You could use P or you could use R, it doesn't matter. Oh my gosh, that was to the right or to the left. 3, 6, 9, 12, 15 to the left. Call that -15. And how many then up? 3, 6. And 6 up. And the R to R prime to R double prime did the same thing. The translation vector then that takes the singles to the double, sorry, the originals to the doubles, like R to R double prime, that went 3, 6, 7 back to the left, and how many up? 3, 6, 8 up. And again, any point should have traveled along the same vector. I think I can do this in 30 more seconds. Okay. The translation that maps that to that, find the vector. Well, it looks like this point turned into this, so it went up by 3 in the X category, and it went down by 1 in the Y category. That's good enough for that. Find the distance from A to A prime. Well, that's just the distance between these 2 points. I'll pause for that. And I get the square root of 10. Now, the preimage of A. What would we have had to start with to get to A after this vector? I'd have to fill in these boxes, and I get -1, -4. Try it. Sorry that was rushed. I got in just in